If you would recall, yesterday we started computing some line integrals, going through the actual mechanics and coming up with a numerical answer. In the examples that we had yesterday, the curve had been parameterized for us, and then I came up with two more paths from the point 0, 0 to the point 1, 1. I came up with two more paths, but only described them, and then so we have to come up with the parameterization. This is not going to be that fascinating for the first one, which is just a line segment from 0, 0 to 1, 1. But the second one, C4, was a quarter circle from 0, 0 to 1, 1. A quarter of the circle that's centered at the point 0, 1. So kind of like this, the bottom right portion of a circle. So we want to talk about parameterizing that. Let's first parameterize the curve C3. It's the line segment from 0, 0 to 1, 1. So we're going from the origin to the point 1, 1. And we're just going to follow a line segment. The reason that I included this one along with the circle one is that this curve we can just represent with this is a portion of a curve, and we can just represent that with this is a portion of a curve that we can represent with a function. We can write it with y as a function of x, which means it's going to be very easy to parameterize. We could just, since y is going to be a function of x, we can essentially use x as the parameter. So since C3 can be represented with a function, writing whole sentences in highlight colors is weird. Since C3 can be written as a function like y equals x, we can just use that function, that independent variable, as the parameter. We can just use the independent variable as the parameter. So our parameterization, let's say call it R3 of t, will just be ti plus t times j for t between 0 and 1. This is just what we did yesterday when we had y equals x squared. We just made x equal to t, and we made y equal to t squared. We're using the independent variable as the parameter. So our x of t is equal to t, and unsurprisingly, y of t is equal to t as well, because x and y are equal. That's the equation, the function that describes this path. The parameterization, we get a little bit more. We don't just get the shape. We get a direction from 0, 0 to the point 1, 1. And we get this segment representing the entire line. The other part that we would need for this, well, we'd need a vector field in which to plug this stuff. But then we'd have a dr. We just take the derivative of each of the components. So the derivative dr, the derivative of t is 1 in the I direction, and the derivative of t is 1 in the j direction. And then this gets multiplied by dt. So this is the direction of the curve at every point on the curve. C4 was part of a circle. The center of the circle was at 0, 1, and has a radius of 1. Well, I shouldn't call it R though, because I'm about to be naming the whole thing R. Radius. And we're still going from 0, 0 to the point 1, 1. What we want to notice here is the same thing we noticed in the previous problem. We can write y as a function of x in this case. Let's write an equation for the circle. And then since we've only got this quarter of a circle, we can actually write y as a function of x. We can also write x as a function of y. And there's two ways to parameterize this quarter circle right away. So we could notice that this circle is described by the equation. Let's see. The x coordinate of the center of the circle is 0. Of the center is 0, so we'll just have x squared. But the y coordinate is at 1, so we'll have y minus 1 squared is equal to the radius squared. So here is a description of the circle in equation form. We have a center at 0, 1, and a radius of 1. Since we have just a quarter of the circle, we can write y as a function of x or x as a function of y. Since we only have a quarter circle, we can write y as a function of x, or we can write x as a function of y. Y as a function of x, then use x as the parameter, or x as a function of y and use y as the parameter. If you're thinking that we should be using sines and cosines, yes, absolutely. We can also use polar coordinates. That's going to be more for us. So if we want to write x as a function of y, then I'll just start rewriting the equation. If I solve for x, we can say x is plus or minus the square root of 1 minus y minus 1 squared. Now, this is going to be the left semicircle and the right semicircle using y as a parameter. The left semicircle for the negative square roots, and the right semicircle is the positive square root. So the negative square root is the left semicircle. And the positive square root is the right semicircle. Since the part of the portion of the circle C4 we want is on the right side, we're going to use the positive square root. Now, if we just have the positive square root of 1 minus the square of y minus 1, that's going to give us the whole semicircle, but we're using y as a parameter. So we only allow the values of y to go from 0 to 1. So to parameterize that curve, one way to parameterize that curve I'm going to use the positive square root of 1 minus y minus 1 squared. Oops. And I'm going to use y as the parameter. And since y is the parameter, that means the y component is just t. This for all values of t, well, all values of t that work. This for all the values of t is going to give us the whole semicircle. But if I restrict my y coordinate, if I restrict t to just go from 0 to 1, that will give us the quarter circle. So restricting the values of t limits us to the lower quarter circle. That is a t. So by limiting the values of t to go from 0 to 1, we're only concerned with the values of y between 0 and 1. So that's going to give us the bottom half of the right semicircle. Similarly, we can do the same thing with x as the parameter. Keep in mind that our x of t in this case, this is what we're going to have to plug into our vector field. X, every time we see x, we're going to have to write 1 minus t minus 1 squared. And every time we see y, we're going to have to write t. So in the vector field we had yesterday, which said 3x minus y as the I component, I'd have to write 3 times the square root of 1 minus t minus 1 squared, I, plus t. At least that part's easy. Then we're going to have to remember that this is going to be, we're in a dot product, and we're going to have to multiply. So, yeah. And we're going to have to integrate. Eesh. Also, our dr I'm going to have to take derivatives of each of these things. So I'm going to have a 1/2, 1 minus t minus 1 squared to the negative 1/2 times the derivative of the inside times negative 2 times t minus 1. All this is just the I component in the dr, the derivative. At least my j component is easier to deal with. I guess the 2's can cancel out. And I can write this as 1 minus t then times the derivative. So I had to take all this stuff to the 1/2 power. So 1/2 this stuff to the negative 1/2 times the derivative of the inside. And the derivative of 1 minus t minus 1 squared is 0. And then minus 2 times t minus 1 to the first times the derivative of the inside, which is just 1. So this is parentheses. And it's parentheses. and then I cancel out the twos. This negative changed the order of the t minus 1 to a 1 minus t, and then this denominator is all a square root. So even after we clean it up, it's still u. It's not that this is how we can, this is how we should proceed. It's not like this is how we are going to proceed, but we should know that this is one of the options. So this is parameterizing with x as the with y as the parameter, and we solved for the x. We can also do the same thing solving for y. dr4, you got the 1 minus t over the square root I plus 1 times j. That was easy to simplify. So we can also solve for y, which I want to do because it's not just as easily symmetric as it normally is by centering at the origin. So solving for y means we'll subtract the x squared and then take the square root and then add 1. So y as a function of x will be 1 plus or minus the square root of 1 minus x squared. That 1 plus or minus is because the center of the circle has been raised up 1. The center at y equals 1. So 1 is in the middle, and we're plus and minusing above that. So this is going to be the top and the bottom semicircles. The plus square root is the top semicircle. And the minus square root is the bottom semicircle. We want the bottom semicircle. So we're going to be using the negative square root. We also want only the right side. And just like we did in the previous parameterization, we'll control that by restricting the parameter to go from 0 to 1. That will give us just the right side. So in the same way, we had 2 choices available for x as a function of y. We wanted the right semicircle. Now we want the bottom semicircle. So our alternate R4 of t. Here we are using x as the parameter. So t times I. We're going to use the bottom semicircle. So I want the minus square root. So 1 minus the square root of 1 minus x squared. That's going to give us the whole bottom semicircle, the left quarter circle and the right quarter circle. But by restricting the parameter from 0 to 1, this makes sure that we only get the right side of that semicircle. Yes. R4, the x should be a t, yes. Yeah. I'll just make it a little bit of a sassy. So this leads to us to similar messiness that we had before because of all these square roots. We have this, this is like one of the reasons that we have to do all this trigonometric substitution, because we keep getting these square roots of squared things, and exponents don't distribute over sums. I wish we emphasized that more. Exponents don't distribute over sums. I wish we would stop doing the distributive property with the friggin' parentheses all the time and start using the distributive property with words. But that's not a fight I'm going to win. So our x of t in this case is the easy one, but our y of t is messy. And finding dr in this case is also going to be messy. The derivative of the the I component is just 1, so that's kind of nice. But the derivative of the j component is going to be 0 minus a 1/2 times 1 minus t squared to the minus 1/2 times the derivative of the inside, which is a minus 2t. Oops, and this is all times dt. And we can clean this up. Yep. Parentheses, 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 close, open, close, close, close. 1 minus t squared all to the negative 1/2, and then times the derivative of the inside, which is a minus 2t. So this is going to be, let's see, the minus and minus cancel out. 2 times a half cancels out. So I have a plus t over the square root of 1 minus t squared. These are the functions that we're going to have to plug into our vector field. We had a very simple vector field yesterday, but we could see how messy this is going to get. Because we're going to have this in a dot product. So kind of big yikes. Even though our vector field is in rectangular coordinates, we're still just describing what x and y are, so we can describe the circle with polar coordinates. We know that our basic circle, centered at the origin with the radius of 1, is x equals cosine of t, y equals sine of t for 0 for t equals 0 to 2 pi. We do want to take the circle and raise it up, translate it up 1 unit. That's not going to change the x's, so x is still going to be cosine of t. But I'm going to want to translate the y coordinate up 1 unit. So instead of just using y equals sine of t, I will add 1 all the way around. So that 1 plus the sine of t translates the circle up, translates the circle vertically 1 unit up. Because we're just adding 1 to all the y coordinates. So instead of the y's going from -1 to 0, they'll go from 0 up to 1. Now, if we just use this parameterization for all the values of t, just use this parameterization for all the values of t, that's going to give us the whole circle, but we only want that quarter circle that corresponds to the 4th quadrant. And so now we have an infinite number of ways to choose t. T can go from -pi/2 up to 0. Oops. Or if we only like to go up to 2 pi, we can start at 3 pi/2 and go up to 2 pi. There are infinitely many choices for describing that part that corresponds to the 4th quadrant. But from 0 to 2 pi gives us the whole circle. We only want that last quarter circle. We should investigate the downstream effects of this. What does the derivative look like? dr. In this scenario, the derivative of cosine is negative sine. And the derivative of 1 plus sine is cosine. Oh. And our x of t and y of t are the cosine and the 1 plus sine. So if, like yesterday, we had a vector field was three x minus y, and x times j. Then if we want to evaluate, we need to evaluate the vector field at R4. That would look like so x is cosine of t. So 3x minus y So this is what our vector field would look like at all the points on the curve R4. Here we are plugging the curve into the vector. What does the vector field look like at all the points on the curve? Now that we have parameterized the curve, here are the vectors in the vector field we want. This is all just standard operating procedure for integration. You're just plugging a bunch of stuff into an expression and adding that stuff up. It's weird because there's nowhere to put the plus sign if we're adding over a continuum, but we've long since gotten over that weirdness. Any questions? How's everybody okay? It's cheating a little bit. I'm like, how's everybody okay? And I took my glasses off and left them off over there, so I can't see anybody's expressions. I can see that there are people in the room, but I can't read any expressions. So it's kind of like, I was like, oh, this way, if you're looking at me and you're all confused, I can't tell. I can't even tell if you're looking. At this point, from this vantage point, I can read none of the signs. I know that that one says exit, and that says periodic table of the element. And I know that that's a maximum occupancy, but I can't actually tell. If you like rearrange the letters, I would not be able to read it. Questions? Slide remarks. For a long time, I thought I was the person that I was amongst all my friends. I thought I had the worst vision. Then one day I accidentally put my wife's contacts in, and I thought I had put both contacts into one eye. It was like, whoa. I was like looking into 3 days ago. I was like, did I put both contacts in? And I like pulled it out. I'm like trying to get the two apart. Then I looked at the packs. I'm like, oh, what is this? I didn't know they made them this big. But yeah, it's weird. I don't know where that comes from because we build in. There's all kinds of prejudice, and I think that you get taught this when you're a student, like how to write things. I've got a trigonometry class, and I don't know if it came up yesterday, but it has to do with like writing, how things get written down. No, it didn't really come up yesterday. But if you think back to trigonometric substitution, and you might make a substitution that says like x equals 3 sine theta, and we might need cosine, but we can write sine of theta is x over 3, and we could say something like theta is sine inverse of x over 3. But when we're integrating, if we've made this substitution, x equals 3 sine theta. Oh, my students would get mad if I didn't tell them that you also have to change dx to 3 cosine theta to theta. Now we're okay. But when you integrate this, you're going to have some combinations of sines and cosine. Sine theta, easy to replace. Theta, easy to replace, but we'd also have to replace cosine theta. And if we have to replace cosine theta, it is completely unacceptable to write cosine of sine inverse of x over 3, despite the fact that it means exactly the same thing as if we did the triangle business. Everybody remember your trig substitutions? Opposite over hypotenuse, square root of 9 minus x squared. So cosine of theta should not be written this way. That's completely unacceptable, even though it says pretty much the exact same thing as adjacent over hypotenuse. No. Yes. So if I saw this, I would say that is amateurish and awful and ugly. But yet 1/3 of the square root of 9 minus x squared. It's like, oh, yes. And then everybody else, like general population, is like, oh, why? Well, because. You know what I mean? I don't know any math teacher that accepts this as an expression from their students. I am convinced is just doing it to be contrary. They're just doing it to be the edgelord math teacher. They're just doing it to be different. They don't actually like that. They just want to be different from their peers. Like, stop trying so hard. Nobody. It's like the only people that would notice are the students in the class. They're like, well, all right, we'll just write this then. And then if those students had to take that class over again and bring it into my class, I'm like, well, what are you doing? And they'll be like, oh, Professor Smith taught me to do this. And I'd be at Professor Smith's door. It's like, oh, what the fuck, dude? And then I would just walk away. That would be the end of the conversation. They would open the door. It's like, oh, Professor Lee, what's up? What the fuck, dude? And I would just walk away. And they're like, oh, what is that about? And when they're like, oh, what is that about? I'd be like, oh, you know what it's about. Well, I'm just keep walking. I'm just kidding. I would never do that. But you're right. Sometimes we look at one expression and say, ah, this is lovely. And an equivalent expression you just say, ooh, that's not acceptable. You know what I mean? But I guess, and in a lot of things, there people will have different tastes. But I think there are certain things we write in math that most mathematicians would be like, oh, ew, that's gross. You know what I'm talking about? Anybody play guitar? Like, PRSs are ugly. I'm sorry. If you like PRS, that's fine, but they are ugly. There's too much figuring on the wood. I know guitar players are supposed to be like, oh, look at the fame and the figuring on the wood. I'm like, oh, God, that's ugly. It looks awful. It's smeared and blurry. I'm going to pay extra for this 10 top. But I mean, that's just my taste. What are we talking about? Oh, yeah. All right. I guess some shit just be too expensive for me. And it's beyond me, and I don't understand. You know, these are crazy guys. Gross. People actually drive these things? That's a joke. No one actually drives them. They just park them in a garage. Which is the most tragic thing that you could do. Or Bugatti Chiron sitting in the garage somewhere. Oh, man, I can go almost 300 miles an hour and you're going to park me in a fucking garage? And on a certain level, the car understands. Like, well, no, the person that has enough money to buy a $3 million car that will go 300 miles an hour is not a person that is in any way skilled enough to drive a car at 300 miles an hour, so they should be parking in the garage, but then they shouldn't even have the car in the first place. But anyway, I digress. You are correct. Some things are considered beautiful in math, and some things are considered kind of ugly, but necessary. All right, that's going to do it for today. That's the idea here is that we have to come up with our parameterization. Don't just get locked into this for one kind of parameterization. It might be that all those square roots actually work out better for us. Kind of doubtful, but it could happen. That's it for today. I'll see you all on tomorrow. Have a good day, and thanks for playing. See you Thursday.